Why, hello there, everybody. What's going on? Welcome back. No, you're not seeing things. This is your math instructor, Daniel Valvo. Even though I said before, I was very excited. I was like, well, I was tired. I was like, oh, math class is over. I made the exclamation. I kind of regret the noise I just made. It was a little different than what I did in class. It's kind of a bad impression of myself. But the point is, I said math class is over. So what am I doing here? Am I apparition? Maybe. But I am still real. I'm still here to teach you math if you want it. Math class, discrete math is over. Everything you technically need, I've already taught in class. I'm just giving you guys a little bit of extra practice problems in case you want it, because we kind of ran out of time today. We're only really able to do one example for all of the one-to-one, onto, and bijection stuff. So I want to do more examples for you if you want it. So if you want, stick around. If not, leave now. Okay, we got rid of them. Let's start talking about one-to-one, onto, and bijections and all that stuff. So what I'm going to do is first I'm going to share my screen. Nailed it first thing down. And the next thing I'm going to do is I'm going to go through a bunch of functions, and we're just going to talk about if they're well-defined, one-to-one, and onto, and prove them all, or prove them if we can, and disprove them if they're not. So we have a lot to do. First up, let's talk about this function right here. F of x equals ln of x. And I immediately regret writing it like this, because I contend the way it's written right now, it's impossible to know whether or not this function is well-defined, one-to-one, or onto. Why? I guess you can't answer, so I'll answer, because no one's here. The point is, we can't tell because nowhere here have I specified the domain or the codomain, right? Remember, we always need, when we define a function, we're not in middle school anymore, when we define a function, we first say what the codomain and the domain is, or domain and codomain is. So I'm going to say this is a function that goes from the domain of 0 to infinity to the codomain of the real numbers, not including 0, by the way. And it does this specifically via the function f of x equals ln of x. That makes me feel much better. So first, let's talk about if this function is well-defined. So really, in this exact problem, we don't have much to do, because this function just is ln of x, so it's going to inherit all of its properties from ln of x. But importantly, we should notice that ln of x is perfect for this domain right here. This domain was chosen very, very carefully for ln of x, actually, because this is exactly where ln of x is defined. Remember, you can't define ln of x for negative numbers. Ln of -4, what's that? Makes no sense. Ln of 0 makes no sense as well. So we don't have ln of 0 or ln of negative numbers, but for anything greater than 0, ln of x is defined. So we should first note for all x in 0, infinity, ln of x is defined. And maybe not more importantly, but equally importantly, ln of x has one output for all these x's, right? And the kind of one reason we can see that is because if you remember the graph of ln of x from like calculus and things like that, the graph looks like this, where this is x, this is y, and this is y equals ln of x. And notice it passes the vertical line test. You might have heard of this before. In the vertical line test, like if you graph a relation like we're doing right here, it must pass the vertical line test to be a function, because passing the vertical line test is equivalent to being well-defined. Why is that? Well, it's easier to see an example where it fails the vertical line test. So imagine you had a relation, I should say, it's not a function, that looks like this. Notice this fails the vertical line test. You could draw a vertical line, for example, right here. Let's say this is at x value, x right there. And then let's say this is A and this is B. Well, this red line is the graph of whatever function we're saying fails the vertical line test g of x. And so what this graph is telling you is that, so on the y we graph g of x, on the x we just graph the input, right? So this is telling you that if you input, actually I'm gonna use a different letter here for x to avoid confusion. Let's say c. So this is telling you is that if you plug in c to g, you kind of get two y values, a and b. This is saying that g of c kind of equals a, and it equals B, where A and B are certainly not equal to each other. And so what that means is G of C has, or G has two outputs when you plug in C, and that's no good. G relates C to two things, not one thing, meaning it's not well-defined. Well-defined means you want every input to have exactly one output. So that's no good. But if you look at our ln of x, the function we actually care about here, this passes the vertical line test, right? Every vertical line goes through exactly one point. And what that means is there's no point you could find down here. There's no point you can find where this x value gets mapped to two different inputs. It just doesn't happen. So that is what it means, really, for x to be well defined. If it is defined and it passes the vertical, if it's defined on the whole domain, if it passes the vertical line test in the whole domain, that means that f of x has an output, but it doesn't have multiple outputs. Therefore, it's well defined. So note, for all x is 0 infinity, ln of x is defined. Further, it passes the vertical line test. So at no point does it have multiple outputs. Thus, f of x equals ln of x relates each input in 0 infinity to exactly one output in R, meaning f is well defined by definition. There we go. So f is well defined, so we know it actually is a function, not just any old little relation, right? It's special. So the point is, it is well defined. Next, let's move our attention, move on to proving or disproving that f of x is 1-to-1. So remember that a function being 1-to-1 means that there are no two inputs that map to the same output. And so there are no two inputs that map to the same output. What that really means is for all A and B in our domain, such that A does not equal B, that implies f of A does not equal f of B. So really, it's a simplification. It's saying that for all A and B, actually, I'll do this correctly. I should say for all A in 0 infinity, for all B in 0 infinity, A not equal B implies that f does not equal f of B. The point is, any two distinct inputs will map to two distinct outputs. They'll map to two different things, not the same thing. That's the whole point of being undefined. And, or sorry, the whole point of being 1-to-1. If you take the contrapositive of this, this is saying that for all A in 0 infinity, and for all B in 0 infinity, f of A equals f of B, negate that, implies that A equals B. And we talked in class why this kind of makes sense. It makes sense because if our function truly is well-defined, well, that means that if you have an A and B such that f of A equals f of B, then A and B must be the same thing because we don't want any two different elements to map to the same thing. So, yes. So, do we think our function here is 1-to-1 is the question. Well, let's kind of draw it again. Think about it. It looks like this, remember? And so the question is, does it look like any two inputs will map to the same output? Well, if any two inputs will map to the same output. Not really, right? I mean, this input maps down here, this input maps down here, this one maps here, and it goes up and up and up and up and up and up and up. But the point is, it never kind of comes back on itself. Like a function that's not 1-to-1 looks like or it might look like this, or it might look like this. The point is it'll fail the horizontal line test. It has to, if it's not one-to-one, because it has to have 2 points from different inputs, right? Different x values, but with the same y value. But that's not how our ln function looks. Our ln function looks like for any 2 distinct x values, we'll have distinct y values. So I should have proved that. So claim is that f is 1-to-1. Proof. So we're going to do the proof like the standard way we talked about, which is technically a contrapositive proof right here. And that is we're going to assume there exist A and B in our domain such that f of A equals f of B. And note we're talking about our function is ln, so by substitution, this means that ln of A equals ln of B. But, okay, actually, let's work with this. Let's work with this. So I'll say note. Ln of A equals ln of B. This implies ln of A minus ln of B equals 0 by subtracting ln of B from both sides. Well, this implies here's the key part, here's the interesting part. Recall a nice little math fact. A nice little math fact that says that the ln of A divided by B equals the ln of A minus the ln of B. And remember this? This is the whole thing with the ln rules. We also have the A times B would be ln of A plus ln of B. A raised to the B is B times ln of A. A bunch of those. And we're going to take advantage of those right now. Because we know ln of A over B equals ln of A minus ln of B, we can run that backwards. Equal signs go both ways, right? So this means that the ln of A over B must equal 0. However, let's remember, right, what ln means. Ln, well actually, we can actually, we'll just do this. Let's do the classic thing with ln's where we raise e raised to that on both sides, right? And this gets us, and I'll say, wait, this is by ln rules. This is by raising e to both sides. And this implies e and the ln cancel out, and we get a over b equals e to the 0, which equals 1. You could think about going from here to here with this step, although I personally don't like this. I prefer to think about what ln of A over B means. Ln of A over B equals 0. Right, the ln of A over B, that means ln of A over B, it asks the question e raised to the what equals A over B. So this means that e raised to the 0 must equal A over B, because remember, ln of A over B, what it equals answers the question e raised to the what equals A over B. So it equals 0, we know e to the 0 must equal A over B. But so either way works. But either way, you get that if ln of A over B equals 0, A over B must equal 1. The other way you can look at it is just memorizing the fact that ln is only 0 at 1. We're plugging in 1. The only thing you plug in ln and get 0 is 1. Either way, you end up with A over B must equal 1. And this is by simplification. And then let's go below the glare. Getting better at this. There we go. End up with A over B equals 1. And then this eventually implies that A equals B by multiplying both sides by B. So notice we started by assuming there's just an A and B and 0 and infinity, it's just that f of A equals f of B. And we've proven A equals B. So what this means is that if we have, if there are two inputs, or if f of A equals f of B, so if these two inputs go to the same output, well, they must not be two different inputs at all. They're just the same number here, A equals B. Therefore, f is 1-to-1, otherwise called injective. All right, soak that in. So ln is 1-to-1. That's great. I guess it's great if you want that. I'm kind of, you know what, it is great. I was going to say that I'm kind of neutral towards math, but I'm not that jaded yet. I care. Ellen's great. I love it. Good for you, Ellen. Now let's go for onto. So recall a function f is onto if for all y in the domain, or sorry, in the codomain, so for all possible out, so remember, like R tells you where the outputs are going to be. So for every possible element in the set of where the outputs are going to be, there exists an x such that f of x equals y. So this says that everything in R here gets hit. Everything in the codomain gets hit. For anything in the codomain, there exists something in the domain, so that f of that equals that thing in the codomain. I think that makes sense. Whereas finding, yeah. So, I mean, let's just prove it. So the proof goes like this. Oh, by the way, I'm sorry. We should first ask ourselves, is ln of x 1-to-1 or onto? And again, I'm going to go to the graph because it's kind of the best visualization we have for ln of x. And if you look at the graph, well, we know kind of this should go down to negative infinity here. So every value between 0 and negative infinity gets hit right here. We also know that f, from calculation, that f is an ever-increasing graph. Like this is not an asymptote. This increases forever. It goes to infinity slowly, but it goes to infinity. So this should eventually hit everything. This should eventually hit all y values from 0 to infinity in the positive direction. So this should be onto. It should hit all the real numbers. So now let's prove it. All right, proof. Our proof goes like this. So we want to prove a for all statement here. So we're going to say is let y be any arbitrary / particular element of the domain, sorry, of the codomain, which here is R. And now we want to show for all y and R, we want to show there is some x such that f of x equals y. Let's look at this right here, right? So f of x equals ln of x, right? So what we're trying to show is that for any y, there's some x such that y equals the ln of x. So what does this x have to be? Like, what's x have to be so that we can plug it in ln and get y? That's the question. Let's just solve for x, right? We can solve for x by doing e to the y, e to the both sides like this, and we get that e to the y must equal x. And we can check this. We can check, and we see that, hey, ln of x equals e to the y does in fact equal y. So this means that there is a number, well, as long as x, as long as this is in domain, as long as it's in our domain, then we've just found an element x in our domain, so you can plug into f to get y. And y was arbitrary, meaning we could do this for anyone. So the only thing we have to prove is that e to the y is actually between 0 and infinity. That's actually going to be a cinch. So I'll say consider x, or I'll say let, we're doing more than considering, we're going to straight up let x equal e to the y. Note, since the exponential e to the y is positive for all inputs, e to the y is going to be in 0 infinity. This is our positive, set of positive numbers for any y. Or maybe I'll put it like this. Notice since the exponential function, the exponential function being e raised to something, is positive for all inputs, e to the y must be in here. So y is this particular element of the codomain, and we note that the exponential function is always going to be positive, because if you look at the exponential function, right, it looks like this. It's always positive. Since the exponential function is always positive for all inputs, it doesn't matter what y is. For this arbitrary y, e to the y is still going to be positive. Yeah, the point is e raised anything is positive, so e to the y is positive. That's all I should say. Anyway, so e to the y is in 0 infinity, which is the domain. Further, f of x, which equals ln of x, which equals ln of e to the y, is going to equal 1. Therefore, there does exist an x in 0 infinity such that f of x equals y. Hence, the claim is true, f is onto. Yeah, and there we go right there. This proves f, beyond any doubt, that f is onto. For anything you pick in the codomain, I can find you an element in the domain, mainly e raised to the element of the codomain you picked. I can find an element in the domain that you can plug into f to get that element in the codomain that you picked. Yeah. So that's that. And I guess one last thing I'll say before we end here is I'll say, note, since f is a 1-to-1 and onto function, f is well-defined. I'm sorry, we already know it's well-defined. F is a bijection. We call functions that are 1-to-1 and onto bijections, or injective and surjective, by the way, we could have called this. Yeah, so there we go. That is ln of x for you. It is well-defined onto 1-to-1, making it an injective and surjective function, making it a bijection. Any questions? Email me if so.